Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, previous session we have discussed about future selection on supervised algorithm. Let me just give you a small input related towards that, and let me have a small summarization. Yes, dear friend, supervised future selection, that is an machine learning, where selection of relevant futures as like variables or attributes or towards the predictors, yes, in your data is guided by the target variable, that is the output of your what you are doing or what do you want to predict. And coming towards that, when I'm just going towards this supervised, yes, let I just give you a clear picture. So here we have supervised technique. Yes, under supervised technique we have three supervised futures technique. One is filter based, and next it is all about wrapper based, and third one it is embedded approach. And dear friends, this exact filter based approach, this filter based future selection approaches are based on data intrinsic attribute such as future correlations or statistics data. And coming towards this, it is further divided into information gain, where this information gain is a statistics that measures the reduction in entropy for a specific futures by dividing the data according to that characteristics. And next it is all about chi-square. So this chi-square test is a statistical test that is used to assess the relationship between two categorical variable. Next it is all about Fisher's score. Fisher's scores is a future selection approach that ranks futures based on their ability to differentiate various classes in a data set. And last but not least, most used, that is a missing value ratio. So this missing value ratio is a straightforward future selection method that makes decision based on the number of missing values in a futures. When coming towards this wrapper based, yes dear friend, wrapper based approach, the future selection approaches includes assessing the importance of futures using a specific machine learning algorithm. When coming towards this wrapper based, of course we have discussed a few more things. One is forward selection. This forward selection, you start with an empty future set and iteratively add futures to the set. Okay, and next it is backward selection, and the opposite of forward selection. So in backward, so you begin with an entire future set and gradually eliminate the futures from it. Okay, and next it is exhaustive future selection. This exhaustive future selection compares the performance of all possible future subset and chooses the best performing subset. And last but not least, recursive future elimination. This recursive future elimination start with the whole future set and eliminate futures repeatedly depending on their relevance as judged by this learning algorithm. So this is what's the main thing which we have already discussed. And coming towards the last type, embedded. Of course, the embedded approach selection that includes the future selection process as part of a learning algorithm, which I have already specified. And yes dear friend, it has mainly two division of embedded. One is regularization. Of course, this regularization we didn't discuss it in detail, but of course regularization is a method that adds a penalty term to the loss function to prevent overfitting in the machine learning model. And next one, it is random forest importance. So random forest computes the future significance score for each future as a part of the tree building process. So which may be used to order a future based on relevance, whether how come it is needed or not. So yes, in the session we are just going to discuss the most important unsupervised. And dear friends, of course, unsupervised, yes, the techniques that allows you to explore and discover important data characteristics without using labeled data. Okay, and here, yeah, we are just going to have mainly 4 unsupervised future selection techniques. And first one, it is principal component analysis. And the next one, independent component analysis. The third one, non-negative matrix factorization. And last but not least, the T distributed stochastic neighbor embedding, which we just shortly specify as like TSNE. Okay, so this is what we are just going to do. So discuss. So let me just go in detail. Yes. Okay. So first of all, let I just have the PZA. Dear friends, going towards this PZA, yes, actually PZA is a linear dimensionality reduction method that converts the original future space into a new orthogonal space defined by this principal component. Actually, this exact PZA, yeah, we are just going to discuss in a detailed manner what is PZA and furthermore. But here, as one among this future selection, I just want to let you know, yes, dear friend, here we are going to have our import libraries, okay, necessary libraries, and we have loaded a data set as like Vine data set. Okay, and we want to see what are all the futures that it has. And secondly, dear friends, kindly just have a note of it. This exact PZA, it is has to further, first of all, it has to make the standardizing of this data. That is, standardize the future. So that is the first main part here we are considered. And once after standardized data, yes, it has to be transformed. Okay, so transforming the standardized data into a principal component. So that is what happened here. And here one more important variable that is we have included here, it is explained variance ratio. Exactly, it just shows how much variance each principal component that explains. Okay, and yes, dear friends, this one we are included here with an output as to make it as like an plotting functionalities. So here we have just given in detail about the plotting. Okay, so kindly just have a note. Let me just see the plot. Yes, so here we are having. And to be one added information, dear friends, actually here we didn't discuss lot about the data. We didn't discuss about what about the attributes are having, or what about the attributes it has, or what about the main feature it has. We didn't discuss, but anyhow with just to have a concept wise. So kindly just have a note on to this. This PZA output is a exact plot that shows the cumulative variance and helps you to determine how many futures or principal components reference your data. So here the exact x-axis represents the number of future, okay, and here the y-axis shows the cumulative explained variance in its y-axis. Okay, so with this, yeah, you can analyze or you can observe, yes, how many future are you going to have, or how are you going to represent. Okay, yes, dear friends, we are just going to discuss it in detail in coming future algorithms. And next, yeah, it is all about independent component analysis. Okay, so this independent component analysis is a future selection technique that helps us understand how different things combine together. See, imagine you have a box of mixed up sounds like people talking, music playing, or cars honking sounds like that. So, this independent component analysis will help us separate these sounds and figure out what each sound is by itself. It sorts of likes listening carefully and picking out the voice or instrument from a noisy crowd to understand what each person's or thing is saying or playing like that. Okay, so here I just want to specify one thing. Yeah, we are making use of this fast IZA, yeah, which is used to perform this independent component analysis. Okay, and yeah, we have loaded the exact data. Okay, so let me just have what is the shape of this data. And yes, here we have the shape. Okay, so of course we have 1797 rows with 64 futures is that. And kindly just observe, dear friends, by using this fast IZA, we are performing this independent component analysis, and we are just transforming and towards the number of components which we are using here is 7 components. Okay, so with the 7 components on this digit data set, let me just see what is the transformed. So kindly just observe, we are just having now with 7. So the goal is to transform the data into independent components. So that is what happened here. Okay, and next it is all about non-negative matrix factorization. Dear friends, this is a non-negative matrix factorization is a method that helps us break down a big number into a smaller positive number. See, imagine you have a big number representing a whole picture, and you want to understand what parts make up the picture. So here this NMF helps us find some small positive number that when you combine them recreate that big number or picture. So it's like taking apart a puzzle and then discovering how the smaller piece fit together to make up that whole picture. So yeah, dear friends, here I just show you this is the exact X component. Okay, and once after making here, okay, so this is what the exact X component, and here we have the H. Okay, so let I just make it into 2 once again. So here we have our X. Okay, and once for all, when you just fit in towards this model, so yes, it is divided into 2, and that is it is reduced into 2, and kindly just to see this one. So this is how the exact model that has been formed towards matrix factorization. Okay, so and yeah, added towards this, dear friends, actually NMF is a dimensionality reduction technique that factor a matrix into a non-negative. Okay, a non-negative, kindly just observe even. Okay, of course we didn't have any negative. Okay, so here we have a non-negative matrix, and which is useful for interpretability in some context, such as like image processing or text processing. Yeah, it would be used. And this exact example shows that this NMF being used to factor a small data set into a two component based. Okay, so that is what we have just provided. Okay, now last but not least, yeah, we are here in T distributed stochastic neighbor embedding. Okay, so this exactly shortly it is specified as like TSNE, and it is also a machine learning techniques that helps us understanding how things are related to each other. And imagine you have a bunch of pictures of animals and you want to see which one are similar to each other. So, well, this exact create a map where similar animals are placed together. Similar animals are placed or conclude or combined. So here, this TSNE helps us visualize and explore similarities. Okay, so here let I just give you, okay, here also we are just making use of this TSNE, and here I have created an array of X. Let first of all, let I just give this X, let me view it. Okay, we are having, this is the exact matrix. And kindly just observe, dear friend, one thing I want to add, this TSNE is a non-linear. Okay, we have seen a linearity. So this is exactly a non-linearity, a non-linear dimensionality reduction techniques mainly used for visualizing and high dimensional data. Okay, and yes, let me just have this execution and kindly observe. We are having actually 3 columns. Okay, so 3 columns, 4 rows and 3 columns, but when we just specify it towards this component 2, yeah, here it is again made it as like a dimensionality reduction technique, and we just got 4,2 with our as a matrix. And yes, dear friend, yes, we are coming to end of this future selection technique. And yeah, this exact feature selection is a vital process in machine learning that involves identifying the most impactful data for model accuracy. So I think this session would provide a comprehensive overview of both supervised and unsupervised future selection techniques. So that is including, we have just discussed both the things. And all these techniques can help avoid overfitting and underfitting, two of the most significant challenge which is in machine learning. And of course, dear friends, we are just going to discuss what is this overfitting and underfitting in for the coming session. Okay, hope, I think so this exact video would be very useful for you. And yeah, see you in the next video, and happy learning, dear friends.